Australian Aviation Podcast, the official podcast of Australian Aviation, unpacking the latest insights, developments and issues impacting Australia's aviation sector.
Hello everybody, my name is Adam Thorn and welcome to the Australian Aviation Podcast. Now this week we have a guest, Jeff Shaknaitis, who is the Customer Sustainability Leader for GE Aerospace, who, as you probably know, are one of the world's most famous aircraft engine manufacturers. And now Jeff's flown in all the way from Chicago, Illinois, in the US to join us today. He himself has an extraordinary career in aviation that saw him rise up from a design engineer working on engine turbine blades to becoming GE's lead fleet engineer and now holding one of the top jobs managing our shift to a sustainable aviation future. And all of this is obviously increasingly important as the whole industry tries to hit net zero by 2050. Jeff, welcome to the show.
Thanks for having me, Adam.
Now, we've got a lot to get into in terms of the company and the stuff you're doing. I want to start off by focusing on you a little bit. You've had this amazing career. Where does your passion for aviation, engineering, where does this come from?
Sure. So really, since about the month I was born, aviation's been in our system. My dad actually worked at GE Aerospace for 30 years. And it's the only company that I've ever worked at as a professional. And I've been here 13 years now or so. So, you know, I was always interested in aviation, but over the past several years, that's really grown as this challenge to work on sustainability has become more and more a part of my career. And when we look at it, this is really one of the most intractable problems that we have to solve. And getting to be here at the nexus of an engineering career and a job in sustainability, working on this problem has just been really, really exciting for me. And being in a company like GE, who has some of the most impressive technology at our fingertips, just a great spot to be right now for the challenges the world has ahead of it.
Talk me through, because you said that it's almost the only sort of professional job you've had or the main place you've been your whole career. How do you kind of rise up the ranks? Because it feels increasingly rare in today's world you can do that, to almost start on the ground and then work your way up. How did that career kind of progress?
Sure, it is. To be honest, it's a very unique situation. I spent my early couple of years as a design engineer, moved into less direct engineering, more customer support engineering roles. But as I was in a customer support role, I was sitting with an airline customer, and this is in the 2020, right around when aviation is really getting its feet under itself and how we solve our sustainability challenge. And I'm recognizing, well, we don't have this capability to interact directly with our customers to help solve our mutual problems. And I was supporting United Airlines at the time out of Chicago and started engaging them on sustainability. And before we knew it, I was leading a 8-month-long project for us to run a 100% SAF flight demonstration. In December 2021, you might remember it, we flew a 737 MAX with 100 or so people on board with 100% SAF and one engine. And over the course of this project, I was starting to recognize some of the facets of how we're going to be able to engage our customers and what competency we need to go build as a business. And so I had written a job description for how to go do this. And it took probably 12 months or so, but eventually turned this hobby project into a full-time job. And since then, I've been waking up every morning with a blank sheet of paper, trying to decide what it looks like and how we're building more institutional capability to work across our customer base, connect that to our product strategy, and ensure that we have that right engagement on all the areas of sustainability and aviation that are material to both us and our customers, so we can be a successful supplier and partner to our customer base around the world.
So I think that's amazing. So it's almost like this was a bit of a side project, almost a bit of a side passion. And you went to the senior bosses and you said, we need somebody just to look after this. Is that kind of how it went down? Because it's amazing that they listened and gave you that opportunity.
That's almost exactly how it went down. The reality is, though, it wasn't, day one wasn't, oh, perfect, well, let's go put it here. You know, it took some time, right? As with anything, we are a very established business, a lot of very established roles and responsibilities. It takes time to think through how we change that. sustainability is a new challenge for aviation. We need to go figure out how to integrate that into our business model and into our strategy. So my role was one of the first of a growing number of jobs in our businesses and the rest of the OEM community, the rest of the aerospace community that are focused on really integrating the traditional business with this new challenge of sustainability.
It's interesting because you're working with the clients, the customers, the airlines, basically. How kind of worried are they about it? Because presumably they're the ones that are kind of pushing this and saying, what solutions can you come up with? Are you sort of feeling that there's more and more and more debate, or there's more and more talk saying, we need to make this work now?
Absolutely. And the airlines know we have this immense challenge ahead of us, right? The reality is, though, they operate airplanes. They fly people around. They don't develop technology, right? They're not oil refiners. They don't have all of this. So they need to go look at the rest of the ecosystem and say, help us. How can our suppliers and our partners across the industry be helping them to solve this problem? So at the end of the day, a lot of the onus is on the airlines, but it is our responsibility, our core responsibility as a manufacturer, to be able to deliver what they need. So really at face value, you see a lot of the onus on the airlines, but recognize across the world, particularly in Europe, some in the US, all public companies are getting pressure both from investors and regulations to decarbonize and plot a path with their product strategy to be eventually net zero. So internally to our company, we have this demand for us to figure out how to decarbonize, but also to go support our partners, our airlines, on their own challenge to decarbonize.
Now, in terms of this show, we've got a kind of a broad range of listeners from all different sort of aspects of the industry, some of which will be technologically minded, others of which won't be. From the outside in, you'd look at it and say aviation hasn't really been disrupted much in the last sort of 40, 50 years. It's kind of been the same to an outsider. And now we've got these challenges of how do we have a sustainability revolution? So let's start with kind of the basics. If we talk about a kind of traditional, maybe old-fashioned aircraft engine, sort of how much CO2 would that produce, and why is it challenging to kind of get that number down?
Yeah. The reality is, airplanes burn a lot of fuel.
Yeah.
Right? I'm not going to speak for the airlines, but on average, the fuel is probably about 30% of the operating cost for your average airline. Give or take 5-10%. So it's an enormous expense. And because of that, the incentive structure for us has always been to deliver efficiency. Because efficiency from our product means less fuel burn, less cost, right? Lower ticket prices for the airline, and an opportunity for growth. And so because of that, though, when we apply the sustainability challenge, we see that the incentive structure hasn't really changed all that much. It's just there's more demand now than ever. So when we look at how do we go decarbonize aviation, it's really difficult to go and say, well, we'll just make airplanes a lot more efficient. The reality is we're already operating on that cutting edge of technology. I mean, gas turbines, commercial aviation engines are some of the most cutting-edge mechanical system technology in the world, right? We have some of the smartest engineers in the world spending billions of dollars a year developing technology for these things. It's not like there's a whole lot of technology just sitting on the shelf that we could go apply, and in the next handful of years, we've made this huge step change in decarbonization for the industry. And so now the question is, well, we were always going to deliver more efficiency in next generation. What else can we add to the list now? What are the bigger changes, the more revolutionary steps that we can take? And those are not easy, and it takes a long time. And so, it's probably hard to recognize for the general public, but the business models that this industry operates in and the timelines it takes to develop technologies are really outrageous when you think about it, right? On the order of decades.
It's a really interesting point you made there, because obviously, the less fuel you burn, the more money you're going to make. So the industry itself has always wanted to have the most efficient system, which is a good point. People don't necessarily understand that. But if you want to make monumental gains, presumably you have to make big advances, big kind of a disruption. How do your teams begin to do that? How do you go, right, almost we're starting again? How do you do that R&D to make those, take us to that next level?
Yeah, sure. So when you think about how we develop technologies, you can go all the way into the universities, into the labs, right? The basements of these technology incubators. Really, for us, that's our research center. That's where, when you think about how we sort of talk about how technologies develop, it's this scale of technology readiness level, right? From 1 to 9. 1 is that university research level. 9 is commercially ready to go on an airplane. So at that low TRL, you're working in the labs, you're working at the research centers. As you get closer, come up to 3s, 4s, et cetera, then you can get into the realm of a lot of the public-private partnerships that we work in, where we have these large demonstrator programs. And we work with partners like NASA, like Clean Aviation in Europe, to put a number of these constituent technologies together into large demonstrators. And this is how we scale and mature technologies through that valley of death. And then eventually, when we see commercial application, we're ready to go put it on a product, then you really take those technologies in-house, you mature them to the point where they're going to have the reliability, the durability that our customers are expecting. You can go put it on an engine and operate 20,000 cycles before taking it off wing. So, but recognize that these are enormously long timelines. Right? We don't develop technologies for engines in a handful of years. Many of the technologies take multiple decades. And we're going to talk a little bit more about the Open Fan and the RISE program. And we started working on this back in the 80s. And it's taken that long for us to develop all the tools and all the materials capabilities that we can finally say we're ready to go bring this kind of technology to the market.
Could you kind of give us almost like the gist, because you'd be able to tell it in a little more detail than me, but almost like the gist of what the kind of recent technological advancements are? I know you've got like your RISE sort of program. What does that say? What's the kind of upshot of how you're able to make that progress?
Yeah. So let's talk about the Open Fan for a bit. Okay. So this is really one of the most revolutionary pieces of technology that we're proposing for next generation of engine. This is where we're going to take the cowling off the engine. You'll have a big, large open fan. It's going to look more like what you see on a turboprop, but not really a turboprop, right? This is the efficiency you get from a turboprop at the speed and the size of airplane of a modern turbofan engine. So if we go back to the 80s, we were developing this technology, and we flew a demonstrator. And actually, the 7J7 program with Boeing was very much going to be a real airplane program if it weren't for the engine really not being ready. And the reason it wasn't is we knew the physics was there, so we tried to go execute it, but we didn't quite have the materials technology. We didn't have the ability to address the noise, the complexity, and the weight. So as we look to today, where we've gotten on the materials side, we have now 4 generations of commercial composite fan blades under our belt, over 200 million hours operating with these parts. So as we're developing the 5th generation for the RISE program, we know how to make a large blade lightweight enough to make it onto a product like this. And similarly, to address the noise issue, we just didn't understand. We didn't have the capability to fine-tune the aerodynamic design to be able to reduce a lot of the turbulence that was driving the noise in these old designs, which were counter-rotating rotors rather than a single fan. So now we've developed, over the years, computational fluid dynamics software to be able to create these models. And now we have access to the most powerful supercomputer in the world to go run these models on. So we're actually running our fluid dynamics, our CFD models, on the largest computer in the world. These are some of the most high-fidelity CFD models that anyone in the world is working on. And that's allowing us to start addressing that noise challenge. And so we're able to achieve noise levels lower than modern turbofans. So through materials, through software, through computational power, it's allowing us to take a sort of fundamental physics problem and actually go execute and engineer that. So these are the tools that are really going to enable us to unlock some of these revolutionary architecture and design changes over the next generation and more of engines.
It's fascinating that you almost said there that they're almost like the crux of the idea, the core thing might have been developed decades ago, but you need other technology to catch up to make it come to life. How far away are we from seeing those kind of engines on modern airliners that you're going to fly in? Are we very close, or is this still something that's way in the future?
Sure. So if I back up for a second, we talked about the RISE program, but just to give you an idea, the CFM RISE program, we're working this with our partner, Safran, part of the CFM partnership. And again, it's not an engine, it's a demonstrator program, as we've always done demonstrators for all of our technologies. And within this demonstrator program, it is the most comprehensive that we've ever done at one time. But we look at, there's 4 different pillars. Number 1 is the open fan, as we discussed. And to complement that open fan, to be able to access that efficiency, we need a much smaller core because your propulsor is more efficient. So we have a number of technologies going into the core of that engine to make it smaller and more efficient. On the other side of it, we have 2 other pillars, hybrid electric and alternative fuels. These are how we start to enable that access to clean energy vectors on the engine as well. So you have open fan, compact core, these pillars to really push the limits of efficiency. You have hybrid electric, and you have capability to utilize alternative fuels like SAF to enable access to those clean energies as they become available.
It's interesting you said that, because I would imagine that in terms of making sustainability improvements, it's a holistic process, and the engine needs to work with the rest of the aircraft for it all to come about. We've obviously had this kind of revolution in lighter and stronger materials in aircraft fuselages. How do your kind of engines work with that? Presumably you have to be working with a plane maker, or you have to be involved so that everything works together as one package.
Absolutely. I mean, just like the airplane manufacturers have been using lighter, stronger materials, we're doing the same.
Yeah.
You take weight out of the system, and that is a good thing for an airplane that needs to get up to 35,000 feet. So, historically, the way an engine and airframe integration works, it is a very close relationship. But in general, the airframer decides on an airplane, and then we have a spec to go design an engine that can be mounted underneath the wing. And that could potentially be interchangeable with another engine as well. A lot of airplanes are dual source on the engine. So as we look at the next generation, though, a lot of the technologies that are going to get us those step changes in efficiency we need are going to require a much more intimate engagement between the airframer and the engine manufacturer. When we look at the open fan, again, we're confident we can go execute this design, but we absolutely recognize there is a challenge of how we integrate it on the airplane. You don't have an engine in a cowl where all the airflow goes under the wing now. The air is going to flow over the wing. That means as you do your fluid dynamics modeling, you need to model what the engine manufacturer is doing with how air flows over the wing for the airframer. And it is essential that if we're going to access the efficiency that fundamental physics of an open fan gets you, we have to get the installation right. Similarly, if we look at some other complex systems like hybridization, if we start to implement hybrid systems, and particularly if we're to implement batteries, well, now you have this degree of connectivity between the electrical systems on the engine, the electrical systems on the airplane that we didn't have in the past. Again, requiring a much more intimate relationship between the airframers and the engine OEMs. So, we're under no pretense that this is easy to do. We know this is hard, but this is why we're looking forward to working with our partners on this. And actually, we have scheduled for later this decade, we have a flight test of the open fan with Airbus to actually go mount this thing on a wing and work with an airframer on how we install it. And these are going to be some of the first sort of proving points where these technologies fly, and we decide, well, can we go do this? Can we go execute this as a commercial program?
This must be really exciting from your team, because I'd imagine they spend a long time, in the hangar, in the factory, or running computer models. The point when you actually see it work, I imagine everybody's very excited for that.
Oh, yeah. I mean, this is just, I can't think of a more exciting time for engineers in aviation, right? We have this incredible problem to solve, technology being at the nexus of it. We happen to be in a really strong position as a business. We have a good order book, a strong balance sheet. We have the capability to go spend billions of dollars to go do this. So being an engineer, GE Aerospace right now, and in the industry at large, we're fundamentally possibly changing the architectures of the airplane and the engine, and some of the most revolutionary design work that has been done in generations. And I'll give you an example, though. As we're running these models for the open fan on the supercomputer, we're actually almost identically matching our test points to the model points. And this is unheard of before, because in CFD, where you have boundary layer separation, you have a lot of turbulence, you need to apply fudge factors to your models. You can't model that. But we're literally able to model now down to almost the molecular level, nanoscale time increments, and we're able to actually model the turbulence. We're able to model these nanoscale vortices. And if you're an engineer working on this, it's incredible to see those data points line up. And so when I talk to our engineering team about this, they're honestly giddy about this technology and what it can possibly unlock for us.
So we've talked a lot there about the engines, about the fuselages as well, but I want to talk to you a little bit about sustainable aviation fuels, which feel that they're going to be a big part of the mix. Yep. How important are they going to be? How much of a difference can it make if you've got sustainable fuel and you've got a more efficient engine? And presumably this is the next step to get there, right?
Yeah, it sure is. Look, let's be honest, right? The airplanes that are getting delivered today are going to be operating in the fleet in 2050. Right? And the airplanes that we're looking at designing for the next generation that may come to the market in the next 10, 15 years, well, those are going to operate into the 2070s or beyond. And likely those are going to burn kerosene as well. So if we're going to decarbonize, SAF is essential. But let's be under no illusion that we're really on track to deliver the volumes that we need for the industry. So there's a whole ton of work left to do. From our perspective, there's a few things that we can really do that no one else can. For one is doing our part with the community qualifying new SAF pathways, ensuring that we're coming to the table and we're helping these nascent producers develop their technology, ensure it can operate in our engines. Then on the design side, right, we want to make sure that our engines are capable of using the chemistries of fuel that are likely to be commercialized over the next decades. And maybe a really important point here is as the global energy system invests in SAF, we need to ensure that there's no risk being added to the cost of development for engines not being compatible.
Yeah.
So we need to really be communicating that we're in lockstep with where chemistry of fuel is going so that we can ensure compatibility. It's
almost like you're taking away the excuse. You can say, well, our engines work with this. How far away do you think we are from seeing kind of commercial flights where we have 100% SAF fuel? So at the moment, I know you get some mixed in, and we've seen a couple of kind of high profile test flights. Now, a lot of this is out of your control because that's about SAF production, about, how much money government's going to put in. But do you think in 10 years' time, it would maybe be a regular occurrence that you're on a 100% SAF fuel flight?
It could be possible. So there's a couple things that need to happen first, though. First of all, we need to allow in the spec use of 100% SAF. Right now, the maximum blend ratio is 50% for most approved pathways. So first step is revising that spec to ensure that we can use 100% drop-in SAF. And that's not that far away because the fuel's going to be drop-in. It meets the same specification, so that the engine's already certified to use it. It's really just allowing that for the fuel qualification. The second step would be what 100% SAF chemistry is likely to be the commercial standard. So at ASTM, we need to go define a specification for 100% non-drop-in SAF first. Then once that's defined, we can go run a certification program to ensure the engine's going to use it. So assuming all of these things happen, there's no reason in 10 years an operator wouldn't be able to use 100% SAF. Is it going to be predominantly available at that point? Yet to be seen.
Yeah.
Right? There's a lot of work left to do.
Yeah.
Likely, we won't be anywhere near 100% on a global level, but in certain pockets, you might be using that. But we really need to be doing this work today and supporting the producer, the technology community at large, so that we can be getting up and starting to scale now, so that when the industry really needs to draw on SAF substantially, right, as the SAF mandates in Europe, for instance, kick in and grow substantially, that feels available. So all the work that we're doing today, right, is gonna help ensure that we're at the right point in that exponential growth curve when the industry really needs it.
It's interesting you say this, because you talk about this with so much passion, and people from outside the industry might go, oh, these horrible airplanes with all their CO2. But in reality, the industry is trying really, really hard and is really passionate and is making improvements behind the scenes. We've spoken there obviously about engines, about SAF, about fuselages, but obviously we've also got sort of parallel to this, another sort of mini revolution in maybe smaller electric vehicles as well for shorter trips, these kind of eVTOLs. Mm-hmm. How realistic is it that they're going to be part of the mix? So is this something that's far away? Is it something you think can work? What's your kind of view on that? Yeah,
certainly. The reality for now is many of these vehicles you see, these startups, they may become commercial vehicles sooner than later. I mean, a lot of it is probably going to depend on how quickly they can certify, but they may be. But let's recognize those as an ends in themselves are not going to solve the decarbonization challenge for the industry. That segment is not where the emissions are. Right? It's in the narrow body segment. It's in the large wide body segment. So the question is, are those actually going to help scale some of that technology to the large commercial segments? And we'll see how all of that plays out. For now, what we're doing is focusing on what kind of electrical systems are going to be relevant for the next generation narrow body fleet. And so for us right now, that means a hybrid electric system integrated into the gas turbine that does not rely on a battery right now. Now, without a alternative source of power like a battery, we recognize there's a pretty modest efficiency benefit there. But because it doesn't require a battery and you get the efficiency benefit, it can earn its way into the engine and onto the airplane without relying on some external technology development that we don't have control of, like how mature batteries are in the next 10, 15 years. Now, once we get that fundamental system into the engine, that architecture, and we learn the control systems, then successive generations, sure, you can add batteries. You can make your electrical system larger. You can make your thermal engine smaller. But we feel we have a path to get that foundational integration of the hybrid electric system into the next generation of engine. That is going to, many different things are going to be able to build on that over different market segments.
It's interesting. You almost talk about those. There's stepping stones to getting there. So when we talk about 2050, that's for those that aren't aware. That's because IATA, which is kind of a global aviation body, has set this goal of trying to get to net zero by 2050. How realistic is that? Is the technology there now, or is it going to require more breakthroughs in future? Is there a pathway to getting to that point?
Sure. So, maybe let's talk about some of the pieces of it.
Okay.
You have efficiency technologies we're working on, and then you have the different clean energy vectors that can support aviation. So SAF, electrification, hydrogen. The efficiency piece, like we talked about earlier, this is the bread and butter of what we do, right? And we're executing the technologies now that we feel are at the right nexus of ambitious and achievable, right? Like the open fan, compact core we talked about. As we get into the clean energy pieces, And this is where some of the challenges are, and we haven't necessarily worked all the incentive structures out. With SAF, it's still far more expensive than fossil fuels. Right? And until, in aggregate, we can close that cost gap through whatever structure of policies, incentives that we deem most effective, right? SAF's going to have a hard time scaling. So we really need to work on that piece. And it's predominantly a regulatory challenge that we need to support. With electrification, really the right incentives are there. As you electrify, kind of like with a car, right? You get this benefit of reducing energy, and it's generally sort of a low cost form of energy. So for us, it's how do we get that technology into the engine, onto the airplane as soon as we can. And some of the infrastructure challenges to then be able to bring electrical power to airports are large, but predominantly solvable in a relatively reasonable period of time. Hydrogen, there's a lot more challenges, right? We have to go create a lot of new technology to put on the airplane. We need to create a certification basis for it. And the energy system needs to evolve so that you have hydrogen available and at an economical price. So as we think about the different challenges with all these different pieces of the puzzle, can we do it? Sure. If we get all the right incentive structures there as soon as we can. But it's not under any pretense that we're necessarily completely on track right now.
It's interesting. So I said before, obviously, you're dealing with the customers, you're dealing with the airlines, you're dealing with your clients. And one of the things that I was kind of told to me about a year ago was that we're going to have pressure globally across all industries to decarbonise, to become more sustainable. But in other industries, it's obviously a lot easier than it's going to be for aviation. So we could have a situation where other industries are making more progress, and therefore kind of global emissions, it's almost like the percentage related to aviation goes up through no fault of our own.
Sure does.
How do you think there is going to be more pressure on aviation? Because on the one hand, it's unfair because you're doing more than any other industry to tackle problems, but you're going to be getting the stick for it. How difficult is it going to be in 10 years' time? Because surely it's going to ramp up on companies.
Yeah, I very much agree.
Yeah.
The pressure probably will grow on aviation, right? And let's recognize now the emissions in the industry year over year are growing. So we don't only need to reduce that growth rate, we need to turn it around. So there's a lot of work for the industry to do, but we really need to communicate how much work is being done and recognize what role aviation does play in our modern society. It's not, you can argue in some sense there is this utilization of aviation by the wealthiest people in the world, right, that fly a lot, but it's become a piece of infrastructure that is essential for modern society, right? And we want to recognize that, but we want to it needs to earn its right to grow and thrive and be a part of a emissions-constrained society in future years, right? So recognizing where we are, one of the world's largest engine manufacturers, right? We have this mandate to go ensure that we can bring as much technology to the table as possible and aid the industry in decarbonizing as fast as we can. At the same time, we need to tell the story of the value of aviation, right? And it's not really up to us. The world will decide how much does it value aviation as it takes a longer time to decarbonize.
It's a really interesting point because aviation is an industry we kind of get a lot of stick, but a world where people fly less is a sad old world. It's taking away the democracy of travel. Because I think a world of cheap flights is a wonderful thing. It's opened up the world. I was talking a little bit, go back to the kind of the RISE program and all the work you're doing on sustainability. Could you give me an idea of almost the kind of the scope and the scale of this? Like, how many people have you got working on this? What kind of, it'd be good to know what sort of you're putting into this in total.
Yeah, absolutely. And like we talked about before, some of these technologies have been in the works for decades.
Yeah.
Right? Many decades. Right now, globally, between us and our partner Safran, we have more than 2,000 engineers working on the RISE program right now. So this is real. It's not on paper, right? And at GE Aerospace, we spend more than $1 billion a year on R&D for technology. So it is fundamental for our business. And I want to be clear that this isn't sort of a side project. This is what we are positioning the future of our business on. So this, when we think of the scale of it, it's hard to think of something larger, right? As in a program that could turn into an engine that replaces the current generation of narrow body engines, right? And we know the scale of that market segment. This is foundational to the future of our business for the next several decades.
It's fascinating you say that, because a lot of people that would listen to this would assume there's 20 or 30 people stuck in an office in the corner working on things. But actually, you're talking about $1 billion, thousands of people. That is a massive commitment. And it was interesting what you said earlier. We have a mandate. Almost we've got a duty to fix this.
Absolutely.
And finally, and time is almost beating us, but what do you think is the future of sustainability in our industry? Say, if we were to do this podcast again, and God willing we will in, say, 10 years' time, where do you think as an industry, where do you think we're going to be? Bit of a curly question, I know.
if only we had 30 more minutes.
Yeah.
But, well, as you think about it over 10 years,
yeah,
right? And remember how long of a time scale that we're talking about it takes us to develop these technologies to ensure that they're ready, they're safe, they're reliable, they're durable, and they're economical for our customers to operate them. So in 10 years' time, I wouldn't be surprised if we are still talking about a lot of these same technologies and a lot of the same tools that we're utilizing now to mature these technologies. But I do expect many of them to be far closer to the point where we can see them operating on a commercial airplane.
Well, on that note, on that positive note, we're going to wrap things up. Jeff, thank you so much for joining us.
Thanks, Adam. Appreciate it.
And we will be back on this show the same time next week. But from now, from us, goodbye.